Well, welcome everybody. Welcome to Café Scientifique. Hi everybody, welcome. Yay! There you go. I was just a little bit too low-key for you, I'm sure. My name is Linda Bowden. I'm the Lifelong Learning Coordinator here, and also the coordinator for the Echo After Dark programs. We're going to get started a little bit early tonight because it looks like we're not getting huge rushes of folks coming in. Generally, how we do these programs is to allow you to have 15, 20, 25 minutes to socialize, and then we start out with the announcements about what the next month's program is going to be before we get into the program itself. So that's how we operate things. The other thing is we have no slides, no PowerPoint. We do have some graphics, and we've got some show and tell tonight, so there are many things to look at. But the whole point is to encourage conversation with these Echo After Dark programs. Now, next month, if you haven't already seen it, our next Echo After Dark on February 9, and you might want to get your phones out for this one, right? It's called February, and we're going to be talking about the science of beer. Well, we're going to be doing more than that. Actually, we're going to be doing some tastings. So this is an Echo After Dark event. We've got folks that are going to be talking about the chemistry of beer. There's a guy coming up from Northeastern University that is actually getting his PhD in the history of beer. Can you imagine? What did you go to school for, right? And then we'll also have some pub games and, of course, some tastings. And for, if you're an Echo member, it's $15 for 5 tastings plus a signature glass. If you're a guest, it's $20. So you might want to get your Echo membership to save some money on all of the Echo After Dark events that we have. And your contributions back there, thank you so incredibly much for that. It helps us to keep doing these programs. And also a big thank you to Vermont Public Television that is webcasting tonight. So all of you are stars also. So very good. Now, just a little bit about Café Scientifique to get you going. You did write down February 9, right? You got that. We don't pay our speakers, and they don't pay us. So this is all about sharing knowledge and conversation and having a great dialogue. We hope that they come with a great point of view. And the first part of the program is where we have the speaker talk about his work for about a half an hour. Then we're going to take a break, and I'd love for you guys to get together. Look at the questions that are in the little on your tables or on your chairs as you sat down. Get together with other folks. Have a conversation about that. Get your questions together. And then after our break and some more drinks from Drink, and also we'll put out some more cheese and hors d'oeuvres. Love to have a great conversation with Carl Brandon, who is our guest here tonight. Like to thank Sigma Xi, who is the scientific research fraternity that has provided us from St. Michael's College with the hors d'oeuvres. So can we have a round of applause for them? They support our Café Scientifique programs that we have here, so we're very, very appreciative of them. The theme drink for tonight is a Cosmo. How appropriate is that? And I was going to tell you just a little bit about Carl, so let me get that information together. Again, there are questionnaires that were also handed to you when you walked in. Because of the fact that we're working on these programs, trying to develop these Echo After Dark programs, we would appreciate it if you could fill those forms out. That's our way of reporting back to the IMLS, the Library Services Program, that has given us a grant so that perhaps we can continue doing these kinds of programs. So your feedback and your email, if you wish to get emails from us just about adult programming, be glad to mail that out to you so you get it before everybody else does. So that would be very helpful. Also, if you want to go to our website for information, we've got links right now for all of some of the programs and papers that Carl has written on our website. So go to echovermont.org/afterdark. You'll see all the After Dark programs that we have coming up, and you can click on that and get links to research papers, also the emerging science that Vermont Public Television put together, a little podcast of that, as well as his bio, questions, and other information. So on each one of the speakers, each one of the events, After Dark, after you've gone to the echovermont.org page, will give you all that information to look at it. So tonight's topic. Topic 23, here we are, the next frontier, Vermont higher education in space. So a brief bio of Carl. Besides excelling in the art of hazelnut cooking, he received his BS in physics from Michigan State University, where he designed part of their first cyclotron, along with his PhD and master's in zoology from the University of Massachusetts in Amherst. He's worked for IBM as a junior physicist and researcher, designing their first memory chip. And for the last 35 years, Brandon has been a faculty member at Vermont Technical College. So he's come all the way through the snow and the ice from Randolph to be here tonight. He teaches physics and spacecraft technology and has developed a new degree program in aerospace engineering and technology at VTC. He's chair of the Aeronautical Engineering Technology Department. Now you know why I started out with the hazelnut cooking, huh? And he recently has been working on a NASA-sponsored CubeSat program, and that's why we're here tonight. This is due to be in orbit in December 2012. So we're hearing about it pretty much first. And it will test navigation technologies to be used in a follow-up CubeSat to be self-propelled to the moon. How cool is that? In his spare time, he is on the board of Opera North, in which he is a videographer. He's sung in the chorus. He's an airplane, instrument, and glider instructor and published chef, excelling in that art of hazelnut cooking. Let's have a round of applause, please, for Carl Brandon.
Well, thank you. What I'm going to be talking about tonight is a topic of CubeSats, which are small satellites that you can hold in your hand. This is an actual CubeSat structure. This was going to be the one we were going to send into space, but we got a new and slightly improved model, which we'll be using, and so this we're using for teaching purposes. And this all happened somewhat accidentally. I was asked to go as the third person who first two turned it down, to go to a NASA Technical Advisory Committee meeting at Vermont Space Grant at University of Vermont. And at the end of the meeting, Bill Lakin, who is head of Space Grant, asked me if I could use $10,000. And I said, sure. And so he said, write up a proposal. And I emailed it in Sunday night at 8 o'clock. 8 o'clock Monday morning was approved. So that bought the first CubeSat kit, which included the structure and the software and some prototyping boards, and got us started on this. It was about 7 years ago. And I've always been interested in space, but my career didn't go that way until 7 years ago. I was working on a variety of other things, as was mentioned at IBM, and I've been teaching, this is my 35th year at Vermont Tech, primarily in physics, but a variety of other courses also. And once I started playing around with this CubeSat stuff, and I started looking it on the web, and I came across a site at the University of Aalborg in western Denmark, and they had a media section with images, pictures, some videos, and including a CAD drawing of a CubeSat lunar lander. So this was a single CubeSat, land on the moon with a little rover coming down on a ramp, and I looked at it and I said, well, that couldn't possibly work. The propellant tanks were too small. They were the size of ping pong balls. But then I thought about it. Would it be possible? So I did a rough calculation and decided it would be possible, and then I did a detailed design for a lunar lander, and this is the result of the design. This is a rapid prototyping model, We have these machines that are like inkjet printers, but they print in plastic and layers and make these nice little toys you can play with and show things to people. And this would be a lander, has 4 little thrusters that would go down and basically follow the Apollo mission from orbit around the moon at 100 kilometers down to the surface. And that, I was just doing this for fun, you know, so that was a fun thing to do the calculations. And, you know, I have a very detailed spreadsheet, so when you adjust the thickness of the tank, it changes the volume and increases the length, and, you know, all of these kinds of things, keep track of all the masses and the calculations for the velocities and so on. So it's a very complicated spreadsheet, and made it a lot of fun to do these calculations. And then I got a call from Bill Lakin one time when I talked about this model at one of the meetings, and he said, well, there's a new grant opportunity that NASA announced, and I think this was with stimulus money, because it was a very short time frame. There were 3 weeks to get in a letter of intent, which told a fairly good detail of what the project was, and then another, I think, 4 weeks after that to get in the detailed schedule and budget. And there were 17 states eligible to apply, but only 8 were able to get grants together in that time period. And we received a grant. We received a $195,000 grant, and that was to look at the technologies that would be necessary to go to the moon. It's not enough to actually build something to go to the moon, but it would be trying to decide what was feasible and what wasn't. And so at one of the CubeSat conferences, I don't remember now what somebody was talking about, but my idea was, oh, somebody would take this to the moon on another mission, and they'd toss it out at 100 kilometers above the moon in orbit, and then it would do its landing. So you'd have to get a ride with somebody else. And then somebody was talking about something, and I said, gee, I wonder if you got as high as a geostationary satellite, the communication satellites, the TV satellites, radio satellites, which are about 22,000 miles above the Earth's surface. Could you carry enough energy in a double CubeSat, which is this size, to carry a single CubeSat and go from the Earth to the moon, get in orbit around the moon? And it turns out you could. And this is the result of that calculation using a bipropellant system of red fuming nitric acid and, nitrogen tetroxide. And I think this one we're using, let's see, I'm trying to remember. Oh, it was going to be hydrazine initially. Then we started looking at some monopropellants as an alternative, which is less toxic. Hydrazine is a very useful propellant. It was used on the Apollo landers. It's used in the space shuttle orbital maneuvering engines. But other than being flammable, toxic, explosive, and carcinogenic, it's not too difficult to deal with. So we were looking at some other propellants developed initially by the Army for use as gun propellants rather than rocket propellants, which is hydroxyl ammonium nitrate and some organic material like methanol. There are a variety of things that have been used for that. So that would be the chemical propelled rocket. The problem is that if you're going to a communication satellite altitude, you're getting a ride with a communication satellite. And these are hundreds of millions of dollars apiece, and they might be reluctant to carry something that's flammable, explosive, and all of that, you know, with their very expensive satellite. I talked to the people who provide the launch services, and we could meet the criteria probably, but it would be very difficult. So the second thing I looked at was an ion drive, where you would take xenon gas and ionize it with an electric discharge and then accelerate it with a high voltage, 600 to 1,000 volts. The ions come out the back of the rocket, and they're coming at about 10 times the speed as the exhaust from the chemical rocket. So they're much more efficient, where this combination here would carry about 1.5 kilograms of propellant, and that would give you just barely about 2,000 meters per second velocity change, which is what you would need. With the ion drive, with a 0.5 kilogram of xenon, we could get about 6,000 meters per second, somewhere between 4,000 and 6,000 meters, which would literally be enough to go from a geostationary launch to the moon, get into orbit around the moon, leave the moon, go to Mars, and get into orbit around Mars, all in something this big. This is the actual size of the spacecraft. So we're looking at those technologies too. Then in the middle, we had a monkey wrench thrown into the works, which sort of derailed the progress on that part of the project, was that NASA announced a launch opportunity. And the problem has been that when CubeSats were first developed about 11 years ago, and the first ones were launched about 3 years after that, the cost for a launch was $20,000 or $30,000. And all the people in the professional space business, NASA, Boeing, L'Oreal, and all these people who make big spacecraft sort of looked at CubeSats and said, well, those are sort of toys and not really worth anything, and they paid no attention to them, just dismissed them. Well, universities started building them, and with the miniaturization that keeps getting better each year in electronics, they were doing real science with these little tiny things. So all of a sudden, everybody else got interested in them. Even National Reconnaissance Office, who does spy satellites, launched 8 CubeSats 2 years ago. They don't say what they're doing with them, but they launched them. They're testing technologies. We're not sure exactly what. I did see a triple CubeSat for sale at the CubeSat conference, again this big, that had a 500 millimeter Maksutov lens and a 24 megapixel camera, and that could look at things the size of cars on the ground. And that's at a total cost of about $300,000 for the satellite, plus the launch costs. What happened when the other people started getting into the satellite business is the relatively limited number of spots for these auxiliary payloads of the CubeSats started going up in price. So today the price is $75,000 to $100,000, which is substantially more and starts pushing it out of the realm of the budgets for universities to be able to do that. So Garrett Skrobot, who manifests large spacecraft for NASA at Kennedy Space Center, said, listen, we're funding these projects at universities, and then you people are not able to afford to get them launched, but yet we pay for launches all the time. Why don't we start putting them on our rockets that we pay for and get them into space that way? And so they put out an initial call for proposals, and I wrote a proposal to get a launch, and it got accepted. So we're getting, and initially they said it was going to be $30,000. And then when they finally, I heard a rumor last year at a CubeSat conference in Rome that, well, that's just going to be if you don't get it to them in time as an inconvenience fee. They're really not going to charge anything. And so when I met Garrett Skrobot in April in California at the CubeSat conference, I asked him that. I said, this is what I heard. He said, that's true. So it's actually, we're getting a free launch worth $75,000 to $100,000 as a result of that grant. So the other things are put on hold. So what we're doing is we're taking the CubeSat, and again, it will be covered on all sides by photovoltaic panels. This is a printed circuit board with 2 photocells on it. These photocells are not what you have on the roof of your house or whatever else you're charging radios with. Those typically run around 13% efficiency. These are 29% efficiency. But as a result, each of these cells costs $300. Now, we were lucky in that we found somebody at the Naval Postgraduate School who had a whole case of them, and I talked to him at the conference last year, and he said, well, how many do you want? And I didn't know how many to ask for. I mean, we really need 12 to cover the CubeSat. And so I talked to the guy who told me about him, and he said, oh, ask for 2 or 3 times what you need. Okay, so 24, 36. Oh, I'll be bold, I'll ask for 30. And so I asked him for 30. He says, well, they come in boxes of 50, so they sent us 50. So we have $15,000 worth of cells for free. So those are the kind of, that part is good. The not so good financial part is all of the components that you want to get for a CubeSat, since they're very small volume and there's not a big market and they require a lot of engineering costs, they tend to be very expensive. So we're a small school, and then we have people working on this at University of Vermont. In fact, Michael Reardon's here tonight, who's analyzing our flight paths to the moon. And then we have people at Norwich University and some students from St. Mike's are all working on this. But we don't have the kinds of numbers of students and the facilities that some of the universities have where they can build all the various boards, all the parts for their CubeSat. So we're buying everything we can off the shelf, and it gets expensive. The basic CubeSat now, to get this box, and there's a prototyping board and some software, is $7,500. The power supply board we have that charges the batteries is $3,500, and the batteries are $1,000 for lithium-ion batteries that have been space qualified. And then we have a radio, a transceiver. It has we uplink at 2 meters, 143 megahertz, and downlink at 435 megahertz. And that transceiver is $5,000. And then we need an antenna that fits on the end of the CubeSat that when we are ready, it deploys 4 little pieces of steel like tape measure for 2 crossed dipoles for our receiver and our transmitter. That antenna is $7,000. And the photovoltaic board that is specifically made to fit on the top of that's another, I forget, it's 2,700 euros or something. So it's, because they've got you. There's no other place you can go. We're using a GPS board in ours, And the board that it mounts on is being made at University of Michigan, and I'm not sure what that they're going to charge us for that. That won't be too expensive. And then the actual GPS unit is Novotel from Canada. Most people here have GPSs, I presume. They typically cost around $100. This board is $900 just for the bare board. And then if you want to use it in a satellite, if you take your GPS and put it in a satellite, it won't work. Because as soon as you get above 60,000 feet or go faster than 1,000 knots, they're required that they turn themselves off, so they can't be used to fly a ballistic missile. So we have to get that restriction removed. And since, again, the only people who can do that are the people who made the GPS board, they charge $1,000 to change that one bit in their software. And then we wanted to run our navigation software on their microprocessor. It's an ARM processor on the GPS board, and they were going to charge us $7,500 to turn that facility on. But it says, oh, you can do it on 10 of them. Well, we only have one. And anyway, we finally got the price down to $375 for getting that facility. Yes.
I was curious, when you wrote the grant...
Well, can we hold questions until we do the break?
Okay.
Just because you've got wonderful things to say and we got to use
Okay. Okay, so and I'm trying to think what else goes in there. We have a little camera that's that's not very expensive, but we're building our own camera board. We have an inertial measurement unit, which has a 3-axis gyro, a 3-axis magnetometer, and a 3-axis accelerometer that's made in Williston at Microstrain, and they donated that to us. That's a $1,500 unit. And I'm trying to think anything else that's in there. And then the boards that are going to go on the outside are actually being made by LED Dynamics, a company in Randolph, Vermont. All former students of mine. Is really nice. They're probably the top high-tech LED company in the world now. They have LED systems on the space station, the space shuttle, lighting whole buildings in Montreal, and they have a lot of experience and expertise with printed circuit boards. So we're going to give them the cells. They're going to mount them on the boards, and we're going to have LEDs on the boards. We'll be the first CubeSat that you'll be able to see from the ground because it's going to have flashing LEDs. You theoretically could see them with the naked eye if you were taking LSD. It turns out that the brain suppresses fewer than 500 photons. That your receptors in your eye can actually see single photons. The brain suppresses them until you get up to about 500, so you don't have too much information. If you take LSD, it turns off that suppression. So people who take LSD describe they're seeing the air molecules. They're just seeing all these extra photons that are normally suppressed. You could see it for sure with binoculars if you could point the binoculars right where the satellite was, which would be very difficult. But I have a digitally controlled telescope which will track the satellite, and that would be very easy to see with something like that. So we'll have the first one. The Vermont CubeSat will be able to be seen from the ground. What we're doing for our navigation system is we're using the GPS, and rather than just the simple GPS, NASA Goddard has developed a very sophisticated system called GEONS, GPS Enhanced Onboard Navigation System. Most NASA satellites are ground controlled, so they're actually navigated from the ground. So they use Doppler radar from the ground and transponders on the satellite in the ground to tell where the satellites are, and then they get controlled from the ground. Well, that's very expensive. You need a facility on the ground. You need to staff it 24 hours a day, 7 days a week. And, they spend millions and millions of dollars on ground costs. Every once in a while you hear them turning off a perfectly good satellite or spacecraft that's in the outer, planets because they literally don't have the money to operate the ground facilities. So they decided to come up with an autonomous navigation system so the spacecraft could navigate itself without having ground facilities in order to do that. And when I heard about that, I talked to them, and the guy in charge of the program said, oh, yeah, you can have that. That would be really good. And then they're patent lawyers. It turns out that NASA has sort of two tracks for projects. One is sort of open source, available to anyone, as most government things are, and some get put on this patent track that they license. And the patent lawyer decided that we couldn't have the source code. So without the source code, they can't compile it for our processor. It was useless. And it took me 6 months dealing with the bureaucracy at NASA, and I finally sort of got around them. When somebody was out of town, I sent an email to someone else of a copy of another email I had from somebody else, and they decided that was enough authorization. They sent us the source code, so now we have it. But that source code, that software, has a very accurate way of predicting where the satellite is, so that even if you lose the GPS for 24 hours, it will be within a few meters of where the satellite's supposed to be. So very, very accurate software for both GPS, and it also can do celestial navigation. It's a little hard to figure out exactly what it does on celestial, and the documentation with the software is 900 pages, so we're sort of looking at that at this point to see what we're going to do with the celestial navigation. If we go to the moon, we're probably going to use celestial navigation, because the GPS at the moment is, well, their software is pretty good. They actually think you can use it on GPS signals from the far side of the Earth that just go around the Earth, the side lobes of the GPS, about 3/4 of the way to the moon. But with celestial, and really all we would need are, and not the stars, we're probably going to work towards that eventually, but just the Earth and the Moon and the Sun, by looking at their relative position and sizes, that would be sufficient to get us to the Moon. Once we get to the Moon, we've got a very clear picture of the Moon. We know where we are there, and that would be something that would allow us to get the final navigation that we would need on the way to the Moon. If we use the if we use the chemical propulsion system here, which I think is not too likely, what that would do is we would take a direct flight path very much like the Apollo mission. So we'd get basically dropped off at the top of a geostationary transfer ellipse. The geostationary satellites are initially launched into a low Earth orbit, maybe a few hundred kilometers, and when they check everything out, then they fire another rocket that puts them into an ellipse that takes them up at the height of the ellipse to the geostationary altitude over the equator, 22,000 miles. At that point, they fire a rocket which circularizes that orbit, and it's now in its final orbit. We would get dropped off there. If we had the chemical propulsion, we then fire that rocket and just head straight for the Moon. On the other hand, if we had the ion drive, we don't have enough thrust to do that, to just go straight to the Moon. So we would stay in that elliptical orbit, and each time we came close to the Earth, the perigee, we would turn on the ion drive engine for about an hour and a half, and each time you would increase the size of that ellipse, and after about 10 months, you would reach about 3/4 of the way to the Moon, to a point called the L1, the Lagrange 1 point, where the Earth's and Moon's gravity balance a satellite so it would stay in the same relative position between the Earth and the Moon as it orbits the Earth. Otherwise, it would have to be as far as the Moon to stay even with the Moon, in which case we don't want it there. At that point, it takes essentially no energy to switch from orbiting the Earth to orbiting the Moon, and so you just fire it around the Moon. In fact, literally at the Lagrange point, L1, if you were sitting there in a spacesuit, you could take the CubeSat in your hand and you could throw it to any planet in the solar system. You'd have to figure out what direction and what speed to do it, but it wouldn't take any more than throwing it to get it there. It's a no energy and no potential energy situation. And you can go from planet to, you can go and find these Lagrange points all over the place. They call it the interplanetary highway. So that's what we would do. That's one of the possible flight paths. And then we'd be in orbit around the Moon, and we gradually reduce the size of that orbit until we got as small as we wanted, and then we take our measurements around the Moon. That kind of flight path was actually done on a Japanese spacecraft in 1991 called Haiten, where they had a rocket failure, and they didn't have enough energy to get to the Moon. And the person who figured out how to do it was actually in charge of this conference where the UVM grad student Michael Reardon, who's here tonight, gave a paper in New York last summer, and Ed Belbruno, and he figured out this low-energy method, and it got the Haiten spacecraft. It took 14 months to get there, but it got there and they did their mission. And so that's one of several low-energy flight paths you can go to the Moon. The high-energy one is the one that would require the chemical rocket. So this would be something that we would most likely wind up doing in the end. If we get the follow-on grant, which we would need, there's a NASA grant that we had $195,000, was called a consortium development grant, where you get multiple schools working together with NASA in order to accomplish some project and get those. The main purpose of the grant is to get those connections established. I mean, you do a project, but the main purpose is the connection building. The follow-on grant would be a $750,000 3-year grant that's renewable for another 3 years, another $750,000, and that would be sufficient to build the spacecraft that could go to the Moon. We wouldn't be able to consider the ion drive spacecraft if we had to develop the ion drive. That's very sophisticated, but it turns out that NASA Jet Propulsion Lab had a project. They developed an ion drive which is exactly the size we need. It's about this big by about that big. It's about 5 centimeters by 5 centimeters. So that's been developed and characterized, and so we would you make use of that. That makes it a feasible thing. We would store xenon in a carbon fiber tank. In fact, we're proposing using carbon fiber for the whole spacecraft. That would save us about 600 grams on the weight of the structure. And in fact, 600 grams is in the neighborhood of how much xenon we would carry. We're talking about 500 or 750 grams of xenon, depending upon the pressure. It would be a little round 9-centimeter tank at 200 to 300 atmospheres pressure with the xenon. There has been a spacecraft that has followed that flight path that we would do, which was the Smart 1 spacecraft built by the European Space Agency. It got a ride to a geostationary transfer ellipse, used an ion drive, and went to the moon. Again, about 14 months total trip time. And that was very successful. When they finished their observations around the moon, they fired up the ion drive and intentionally crashed it into the moon. That was a big enough spacecraft, about 760 kilograms, about 3/4 of a ton, that the flash of the thing hitting the surface of the moon could be seen from the Earth. But we would have, instead of 760 kilograms, we would have about 5 kilograms. So it would be a very different scale, but the same kind of flight path. And I've already talked to some people about what instruments we could put in there. There have been some very sophisticated instruments developed for CubeSats. MIT is working on one right now. They got in the CubeSat game rather late. They just really started this past year. But they're a typical MIT. They're doing a very sophisticated project. They're building a triple CubeSat that would basically, not quite as sensitive, but it would do the same kind of work the Kepler Space Telescope is doing, look for exoplanets, planets around other stars. So that's an idea of the sophistication that could be done. I saw a scanning ultraviolet spectrometer on the size of the single CubeSat like this that was part of a triple CubeSat that was going to be looking at Earth atmosphere stuff, but you could look at the moon. Just lots and lots of stuff. We would basically have about this much space for instruments at the end of the propulsion system. And how's our time? Do we talk some more about it?
We've got about five
okay.
minutes if you want.
So there are a bunch of people that are working on CubeSats around the world. There was, unfortunately, let me try and remember when that was. It was must have been sometime last fall, no, a year ago last fall. There was a launch from Alaska on a Taurus rocket, and that actually had the shroud. These rockets that carry satellites have a shroud that covers the satellites at the end of the rocket. The shroud is actually built in Bennington. There's a company called Vermont Composites. I'd never heard of them until I heard about this thing. What happened is the shroud didn't separate. They don't make the separation mechanism, so it wasn't their fault on the separation. And what happens is that, if the thing had not separated, you couldn't release the CubeSats. But it turns out that separating and dropping off the shroud is actually necessary to get the mass of the rocket low enough to get into orbit. So they went right into the Pacific. They were launched from Alaska. So actually, one of the slides at the CubeSat conference, the guy was supposed to talk about the results from this project. He had a picture of a CubeSat with a little snorkel and propeller on the back and bubbles coming out of it. So the first submarine CubeSat. And it turns out that's the second failure of Taurus XL shroud separation system. And they put in a second, totally different. They redesigned it. And it also failed to separate. And I'm guessing that they may have had a software problem. Now, one of the things that we're doing that is unique is we're using most CubeSats, not what we're doing, most CubeSats use C as the programming language for their CubeSats. Problem with C is it's probably the most unreliable language there is. You can do all kinds of really bad things with it, and the language compiler itself doesn't find these bad things, and your software just doesn't work. And when you've spent, maybe $50,000 on parts and, $75,000 or $100,000 for a launch and 5 years building your CubeSat, to have it fail because somebody exchanged a period and a comma, which actually caused the Mariner spacecraft to crash into the sun many years ago, that you don't want to have that happen. So we're using the language called Ada. It's a name for Lord Byron's only legitimate daughter, Ada Lovelace, the Ada Augusta Countess of Lovelace. And she is considered to be the world's first computer programmer by virtue of translating a lecture about Charles Babbage's mechanical difference engines in the mid-19th century and then putting in all this notation on how to program them, which nobody had figured out. And so the language was named for her. Its specialty is initially was developed by the Defense Department to do embedded systems, meaning a computer that's part of something else like a missile or a plane, kinds of things the Defense Department does, or your washing machine or your microwave or your car, or virtually everything today is an embedded computer system, unless it's just a desktop computer or a laptop. And that language has been developed since 1980 and been several modifications. And it's so reliable that all airliners, avionics are programmed in Ada today. Every manufacturer uses Ada. All the air traffic control systems are done in Ada because the word, you know, when your computer crashes, crash and airplane doesn't go well together. So we want to use a language where that's not, your computer crashing is not what's going to happen. And in addition, there's another tool called Spark, which is a static analysis tool. What that means, it analyzes the program without running it. So before the program even runs, this checks the program and actually proves that it's correct. Well, the first time you use it, it tries to prove that it's correct, and it tells you how many of the proofs it could actually prove. We did a previous project on an Arctic sea ice buoy. There were 750 verification conditions it tried to prove. It could do 3/4 of them. And then every place it couldn't prove it, there was a problem. And some of these problems are so subtle, there's absolutely no other way you'd find them, just sometimes the software wouldn't work correctly. So we're using that tool. That tool used to cost $120,000. The people who make our Ada compiler, who have an open source model for their business model, and they sell their support services, they convince the Spark people to do the same thing. So instead of selling it for $120,000, you can download it for free. Get these tools, which are just fabulous tools for almost any kind of project. The whole Ada development environment is freely downloadable, and you can use that. And I think the Spark people were able to make that decision because they got a contract to build the next UK air traffic control system. It's probably a $50 million contract. So, but anyway, they did it, and when they did that, the CEO was talking at a Ada Europe conference in Scotland I was at this summer, and he said that was the best decision they ever made because now people in universities are using their stuff, suggesting improvements, and they've actually increased their revenues compared to when they were selling it for $120,000 a copy. Now they give it away, they make more money. So this is an interesting business model which has occurred, and these two companies, AdaCore, who makes our Ada compiler, and its Praxis high-integrity system that does the Spark system, are now making, you know, lots of money giving away their products. So it's an interesting thing that's happened with the whole open source world. People in general, that tends to make, there are exceptions. We actually have one at our school, the academic software that's open source, but generally it works out quite well to get very accurate, very reliable software. So that's what we're doing with the first CubeSat project to use Ada. It turns out that there is no Ada compiler for our processor. We're using a Texas Instrument MSP430. They're used in all kinds of appliances. They're fairly inexpensive. Their key is they use very, very low power, the lowest power processors, and we don't have a lot of extra power. But I came up with the idea, knowing about a product called Ada Magic, which would take as the front end of an Ada compiler. All compilers have a front end. They produce an intermediate code, some kind of intermediate language, and then they generate the code that runs on the machine with the back end. This one produces ANSI standard C language for the intermediate code. So I came up with the idea of writing in Ada, running it through Ada Magic, and then using a C compiler for our specific processor. I gave a talk at the Ada Europe conference in Venice 3.5 years ago, not knowing if it would actually work. It was a proposal. Well, it turns out we've been doing it and it actually works. So it's sort of a neat project. I then talked to the Praxis people, and they actually did the same thing for a totally different purpose. A customer came and asked them to make a high security system. They wanted it programmed in C and designed in Universal Modeling Language, UML. High integrity in C is an oxymoron. So they wrote it in Spark Ada. They ran it through Ada Magic, delivered the C code, ran it through a UML tool that would work in reverse, took the Ada code and generated the UML design language and the documentation. And although the thing was actually written in Ada and Spark, the client never knew that. All they saw was the UML and the C. But it was C that was actually correct and worked the way they intended.
Well, thank you very much, Carl. Can we give him a round of applause, please?
Thank you. Thank you.
Excellent. Where are we going to start? Who's got the first question that would like to be asked? Yeah? Okay. Right here?
Question. Where does the energy come from to run the ion drive? Is that strictly from those solar cells?
There will be photovoltaics. Now, on an ion drive spacecraft, we would have fold-out panels. So we'd probably have something 30 to 50 watts worth of panels. So each panel the size of a triple CubeSat will hold 7 or 8 cells, so 7 or 8 watts. So we can, there already are some fold-out panels for sale. Both CubeSat Kit, who makes this little thing as a fold-out panel, and a company who makes our antenna, ISIS, in Holland, has fold-out panels. Or you can make your own. I mean, that's something that is a structure that wouldn't be too difficult to make.
Okay. You have a question over here?
Could you talk a little bit about the effects of radiation and how that affects your ability to use electronics? Because my sense is that most of the electronics that we use now off the shelf would not function in your environment.
Excuse me. For our that was me. For our spacecraft, which is a low Earth orbit, we're going to go to 325 kilometers, and low Earth orbit CubeSat's up to 700 kilometers. Nobody's used radiation-hardened hardware. Nobody's had any problem. Where you run into problems is when you start going further and going through the Van Allen radiation belts. Now, if we go to the moon, we're going to be going through the Van Allen belts a lot. And so part of what the UVM group is doing is modeling the radiation environment to see how much radiation there is. And there are several strategies you can do. You can put shielding on parts of the structure that is most sensitive. You can turn off the electronics when you're passing through the high radiation environment. Or you can buy specially radiation-hardened chips. It turns out that the big problem with radiation is not physical damage, but in the microprocessor particularly, you can change a bit in somewhere in the logic by the radiation going through. And there are two types of changes. There's a single event upset where you just change something and it screws up what the software is doing, but it can be reset automatically. That's not a problem. And some logic designs, you can have a single event latch up where it actually puts it into a state where it can't recover, can't change. So the radiation hardened, they just design the logic so that's not possible. So they spend extra engineering money to do it, and it's a fairly small market, so they charge a lot for it. Although we could probably get radiation-hardened microprocessors as donations, if we came to that. We'll put their logo on the outside.
Okay, we've got a question in the back there.
Thanks for your talk, Carl. I'm wondering, imagine we found out there was an asteroid coming towards the Earth. It's going to be here 10 years from now. Could these, you said it weighed about 5 kilograms, could CubeSats be used as some sort of gravitational tug?
Well, 5 kilograms is not a lot of gravity, and if you pushed on it with the ion drive, it's pushing with a force sort of equal to the weight of a dime, not very much. So that's probably not a good use for CubeSats. You might be able to use CubeSats with cameras in them to look for asteroids. That's a possibility. If the MIT group's going to be looking for exoplanets, there's probably a similar amount of sensitivity for that job as well as looking for asteroids. I have somebody handed me a written one, which I'll read. And it says, if CubeSats start filling the Earth's orbit, does CubeSat protocol require forced reentry burning up in the atmosphere? And would this Earth's ion belts change over time due to this? There actually, at the moment, is not a very strict requirement. If your CubeSat is likely to be up for more than 25 years, you have to do something to bring it down by 25 years. If you take a single CubeSat and you put it into an orbit of around 700 kilometers high, of which a number of CubeSats have been done, they last about 25 years before the combination of the very small amount of atmosphere and the radiation pressure from the sun causes them to re-enter. But there are already several commercial products you could buy for your CubeSat and several experimental things that will cause them to re-enter quickly. One is a tether, where you have some kind of wire or conductive strand that is ejected from the CubeSat, and as it passes through the Earth's magnetic field, it acts as a generator, generates electric current. And then you just dissipate that electrical energy in the CubeSat with a resistor or something, and that energy comes out of the kinetic energy of the CubeSat, slows it down, so you can re-enter a CubeSat in a matter of a few weeks. And there are two products available now. One is like a spool of thread. It's a spool of wire, which is spring-loaded, and at the appropriate time when your mission's over, you just release it, and it gets shot out the side of the CubeSat, strings out this 50 or 100 meters of wire, and the CubeSat comes down in a couple of weeks. And there's another one, which is an end plate that has some sort of conductive fabric strands. I don't remember how long that one is, that it get ejected and do the same sort of thing. You can even use tethers in reverse direction in that you can take energy from your photovoltaic cells and run them through the wires and have the thing act as a motor against the Earth's magnetic field and use it to keep the CubeSat up or raise it in orbit.
Wow. Okay. Any other questions up here? Yeah.
I realize that you're using or you're hitching a ride for this particular experiment that you guys are working on, but could you talk a little bit about what type of energy it takes and what the process is for lifting off the surface of the Earth if you're going to go on your own?
Yeah. What you need to do to get into low Earth orbit is you need to get at a velocity of about 8,000 meters per second, about 8 kilometers per second, about 5 miles per second, 18,000 miles an hour. And at the moment, so far, that has required a minimum of a 2-stage rocket. Some of the rockets that have done it have been 3-stage rockets. In the Apollo missions, they used 3 stages to get into Earth orbit, and then they used that 3rd stage to leave Earth's orbit and go to the moon. But there was a proposal to have a single-stage launch to orbit that was being worked on, but got canceled by NASA. You know, they were having some technical difficulties, and they just didn't want to spend more money on it. The rocket that we're going to go on is a Falcon 9 made by SpaceX. SpaceX is a company founded by Elon Musk, who took the $1.2 billion he got for selling PayPal to eBay, and has a lot of fun with it. He's building rockets, and he bought Tesla Motors, which makes, you know, electric cars that compete with Ferraris in performance. He's not a rocket designer, but he had a lot of money and he's a clever guy, and so he hired the top rocket designers from all the rocket companies and says, here's lots of money, make something that's better than anybody else's, that's more reliable than anybody else's, and is cheaper than anybody else's, and he has succeeded. He started with a Falcon 1, which had a single, their kerosene liquid oxygen engines similar to the first stage of the Saturn V, but much, much smaller, similar to the engines used on most of the Russian rockets. In fact, it may have been derived from a Russian rocket, I'm not sure. And they simplified the design and made it more reliable. Instead of 2 separate turbo pumps for the propellant and oxidizer, they have a single shaft pump and things like that, which reduce the cost, increase the reliability. And the first rocket, the Falcon 1, had 2 identical engines, one in the first stage, one in the second stage. And then that was a relatively small rocket that would go into orbit. The second rocket is the Falcon 9, and that has 9 of the same engines in the first stage and 1 in the second stage. So every time they have a launch, they get experience of using 10 engines. So they get to improve their reliability, learn from any problems that they have. So a lot of very clever things like that are being done. They just announced a few months ago the Falcon 9 Heavy, which are 3 Falcon 9s strapped together. The center one being the second stage. They use the fuel, the propellants from the outer 2 stages to feed all 3 until the outer 2 run out of fuel, and they're discarded, and the third one is now, the center one is now full, and it acts as the second stage. That will lift 54 tons into low Earth orbit, about twice what the space shuttle did, but still, the amazing thing, it's only half what the Saturn V did. And you know so basically you need a 2-stage rocket, and it has to do with, it's more the details are in the rocket equation with the mass ratio of how much propellant you have compared to how much non-propellant in the rocket, and what velocity you can get. And typically you need to get 2 stages in order to do that.
Wow.
Okay, well, whoops. I'm not a rocket scientist, so I was wondering if, in layman's terms, you can explain the future applications you see for the CubeSat. So, for example, what other types of data would you expect researchers to be collecting?
Well, most of the things, and it's probably true, it's probably a general statement is correct. Probably most of the things that we use satellites for observing today, big satellites, expensive satellites, most or at least many of them can be accomplished with CubeSats at a much lower cost. You can buy a triple CubeSat from CubeSat Kit that's ready to go. It's got everything in it, but it's got a space about this big to put your experiment in. But it's got the power supply, it's got an inertial control system to keep hold the attitude where you want it, and it's got fold-out photovoltaic panels, so it's got lots of power, and it's $300,000, ready to launch. And if you just wanted to use it and have a satellite in orbit, and a big one, that's what it would cost you, plus the launch costs. So that's a triple CubeSat, so the launch would probably be $250,000 to $300,000. So you're still, much under $1 million, and most satellites start at like $50 million, and the launch costs start at $50 million. Now, the SpaceX Falcon 9 rocket, their launch costs that they are advertising now are 1/4 of what Boeing charges, because of the way they're doing stuff is just much lower cost than all the other rocket companies. And so costs, will be coming down. And we're lucky we have a free launch, but.
And Carl, I think you and I had a conversation about how they might be elements of food packages or things like that on the way to other kinds of locations, or what else could you use, to follow up on your question? What could we anticipate? Why would we want our own satellite? And then what could we anticipate using it for in the future, kind of thing?
Well, I mean, even the CubeSat we have, it's going to be a too low orbit to be used for much other than what we're doing it for, because it'll be, they're testing this Falcon 9 rocket with a Dragon capsule. A Dragon capsule is intended to carry cargo to the space station or 4 astronauts to the space station. And we're on the astronaut version test flight. We're the first astronaut version test flight. So for that kind of launch, where they're specifically making this test, it's below the altitude of the space station, which is 400 to 600 kilometers. And our CubeSat, if we get its mass up to the maximum, which is 1 1/3 kilograms, will stay up for about 55 days. And if you got up, but the time goes up very rapidly with altitude. So if we went up to 375 kilometers, it might stay up for 4 months or 6 months, and so on. So, and if once you get up to, like 500 kilometers, you can be up for 10 years or something. Once you're at that altitude, you could use it as a communication satellite. This thing does have all the capabilities for a communication satellite. It has a radio receiver and transmitter and the power to run them. So that's one application. And there are, a number of third world countries that are putting up little tiny communication satellites. A number of CubeSats have gone on missions with some of those. Some of the other launch vehicles that CubeSats have been on, actually the Falcon 9 has launched more than any other so far. Ours will have 4 launch boxes. The launch box is the size of a triple CubeSat. It will hold 3 singles or a triple or 2 1.5 or a 1 and a 2. And they're called P-pods. They're developed at Cal Poly. And they negotiate launch space and prices with launch operators. And so this will hold 4 of them. There'll be 3 of them holding 3 CubeSats each, so there'll be 9 single CubeSats, and the 4th one will hold 2 1.5 length CubeSats with a tether between them, which is doing some experimental work with tethers called TetherSat. So besides communication, again, as I mentioned, the MIT one's going to be looking for planets around other stars. There's a one that was launched by University of Michigan. They actually have their 2nd version is up right now called RAX, which is the Radio Aurora Explorer. And they're using high-powered radar in the ground in Alaska, and they have several, satellites will pick this up in orbit, and by that, determining what happens to the radio signals, analyze what's going on with the ionosphere, which is important for various types of radio communications. So lots of research projects. And again, as I mentioned, there's a triple CubeSat with a camera. You want to do mapping and take pictures of stuff. It's not as high resolution as the $1.5 billion spy satellites, but it's only $300,000. And you can put up a lot of them. One of the advantages of CubeSats, one of the reasons the big satellites cost so much is they really have to be reliable. When you have a failure of a $1.5 billion satellite, somebody's going to be in big trouble. Where instead, you send up 10 $500,000 satellites. If 1 or 2 of them fails, it's no big deal. So that's another thing. That CubeSats can actually make the total cost less, because so much of that cost on the big spacecraft is for reliability, which is not needed on inexpensive spacecraft. But nobody had done inexpensive spacecraft before. They've always done big stuff. And SpaceX with the Falcon 9 is the first non-governmental entity to launch a spacecraft into orbit and recover it. They had the Dragon capsule. They launched it. It made a couple of orbits of the Earth, and it landed right off shore of Los Angeles where their offices are. They just had to go out in a boat and pick it up. And it came down. It looked just like the Apollo missions, the 3 parachutes, and I mean, the shape of the capsule is slightly different, but other than that, it's pretty much the same kind of thing that was done with Apollo.
So it looks like you need to put your order in right away. Are there questions up here? How about back there? Yeah? Okay, Sarah, how about that?
So with respect to the chemical engine, which you said you're not going to use, how does the thrust-to-weight ratio of that compare to something bigger like one of the Apollo missions?
The thrust-to-weight ratio is probably, let's see, we were looking at, it's going to be less because we're looking at landing on the moon, not taking off from the Earth. It'll be similar to what the lunar lander was. I was looking at 4 Newton thruster for the 1 kilogram satellite. It lands, it's about a half a kilogram when it actually touches down. And on the Earth, a kilogram would be about 10 newtons. So it would be 5 newtons when it was landing on the Earth, but it's landing on the moon is much less than that because the lunar gravity is about a sixth as much. But the mass ratio of the propellant to the spacecraft, when I did the calculations, I was able to check them by looking at what the lunar lander was for the Apollo mission. Mine was within 0.2% of what they used. So that made me confident that I was doing something right on the calculations.
Can you talk about how you collaborated with, I guess the UVM is also part of this, and the other parts of the consortium, and was that written into the original grant, or is that something that you gathered? And talk about how Vermont became involved and how you're helping put that all together.
Well, it's part of the original grant. Well, I had these small grants. I started collecting some of the CubeSat parts, but then we got this consortium development grant whose purpose is to get different organizations working together. Because, for the size of our state, we have a fairly active Space Grant Consortium. Bill Lakin, who's a retired UVM professor, runs that at the moment. And Junyu, who's the associate director, is a math and engineering professor at UVM. And he's working on our project specifically. And I've been going to these NASA Technical Advisory Committee meetings for several years, and I knew these people from Norwich and people there since we had these connections already. And I had actually done a project for Junyu before. We were doing something for him at Vermont Tech. That when this opportunity for this grant came out, we didn't have to try to find people to work on it. We had people we could put together very quickly, and it really had to be, we basically had to put the team together in a few days. And we did. And we got I wrote most of the grant, and Bill Lakin did part of it, and we were the two primarily who did it. And then we got the grant, which was very nice and surprising. And once I got that thing, we're looking at going to the moon. It really did affect the way I see the moon. I look at the moon and I just sort of stare at it all the time. That something that like this that I built with my hands could be orbiting the moon in 6 or 7 years, and will be orbiting the Earth by the end of this year. Which is I still have a hard time, imagining that. And I didn't bring it along, but I have a Lego model of this that my 7-year-old son built. And he's very interested in space. He loves to watch the NOVA astrophysics programs. And
wow, I had no clue. And what an opportunity you're giving to so many students of being able to work for NASA. I think that's awesome. Yeah. Any other questions up here? How about back there? Yeah? Yeah? One other question? Sure.
Not something that seems to be particularly relevant to tonight's discussion, but about space elevators and how any such space elevator would deal with the problem of both intentional orbit stuff and space junk.
Well, space elevators, most people probably don't know about them. The space elevators are a really neat idea. Basically what you do is you put a satellite up in geostationary orbit over one position over the equator, and then you lower a tether, and typically what they're looking at is a carbon fiber ribbon, might be a meter wide or something like that, very, very thin. And the current carbon fiber technology isn't quite up to the job yet, but they're expecting within a few years that carbon fiber made from nanotubules will be strong enough that you lower this down to the Earth. Now, the weight of this ribbon, as you lower it down, allows the satellite above to go higher, and basically the center mass stays at the geostationary. It's not quite that, but close to that particular position. And then what you can do is you now reel it out further, and it puts tension on this tether, which is attached to a floating platform like an oil rig somewhere on the equator. And then you have a thing with rollers that literally climbs up the tether with your satellite. And one of the proposals is to power that with a powerful laser beam from the ground, so you get very high intensity on the photovoltaics. You don't need so much of them in mass. And that thing will climb up into orbit. And the possibilities of reducing the cost to get something in orbit are enormous. If you let the tether get longer and longer, the velocity at some point you get to the top of the elevator is escape velocity. And then things can climb up and you just release them and they can go to Mars. Now the problem is, there are a couple of problems. One is you have to worry about thunderstorms. If you hit a very thin carbon fiber tether with lightning, it's not going to be around. But the thunderstorms, out over certain parts of the ocean are fairly predictable, and you literally would move the platform around to stay away from them. What you're asking about, what about if space junk hits it? And so some of the people who are doing tethers now, the tether sats, have actually looked at that. They make a wide fibrous tether. And the one that was launched a couple of years ago, it then had a little crawl. It was two single CubeSats with a crawler in the middle. And they separated, 50 meters. And then this crawler went across with a little microscope camera, kept taking pictures of the tether to look for damage from micrometeorites and other things in space. I mean, you could get hit by something big and ruin it, and wreck it. But, they think people are looking at the statistics, and it looks perfectly doable. So for space elevators, it's really a matter of getting the carbon nanotubule fiber technology strong enough. It's getting there, and they have some initial competitions now where they have the climbers and stuff like that. And they have competitions NASA puts on every year for some of the technologies, and they keep getting better and better at it. But that's something that may be in the future. It'll greatly reduce the cost of getting satellites into orbit. And when I answered the question earlier about deorbiting the satellites, there is talk about putting a requirement in that less than 25 years, so that a much shorter time frame, that after a certain period of time, if your mission is over, you have to have deorbiting capability. Besides the electric tether system, there's some other very simple ones. We just have a mylar balloon which gets inflated with some butane or some compressed gas, and a balloon this big on a CubeSat this big will cause it to come down in a couple of weeks. So that's another way to bring it down.
You're welcome to make comments, too, if you want. You don't have questions, but you'd like to make some comments? Okay.
Aside from the great decrease in the cost, what are the benefits of sending a CubeSat to the moon, and what would be the scientific objective of having one, and what would it be able to do that something larger couldn't do with whatever sort of instrumentation they would send?
As what it could do that larger ones couldn't do, it might do something that they aren't doing with larger ones, not that larger ones couldn't do. For example, I have a friend at NASA's Jet Propulsion Lab who does photometry of various solar system bodies. And so he's trying to look at the brightness of a planet or an asteroid and determine what the actual stuff is they're looking at. And on the moon, we actually have places where we had astronauts standing there with a camera taking a picture between their legs of what the surface was, and then scooping up that surface and bringing it back. So we know exactly what that image relates to. So he would like to take pictures of some of those sites from many different angles, and no one is doing that. Right now there's the Lunar Reconnaissance Orbiter is going around the moon, mostly taking very good pictures. And then there's the Grail spacecraft, which are on their way to the moon now, which are gravity sensors. They measure the distance between themselves to within a micron when they're several kilometers away. And by looking at the change in distance, they can map the gravity of the moon very, very accurately to determine its subsurface structure. So some of it could be things that could be done on a bigger spacecraft but aren't. And, as opposed to, the Lunar Reconnaissance Orbiter, I'm guessing, is $1.5 billion spacecraft, just from its size. I saw it. It's about a 10 or 12 foot cube. I saw it down at NASA Goddard before it got launched. It was about to be vacuum tested, and this big giant thing is sitting there. Boy, they're going to launch that and get it to the moon. That's the big piece of hardware. And the other thing is I got a 50-page document from NASA on what they would like to measure on the moon. And so there are lots of things that could be done. If we have the ion drive orbiter, we're going to have a space like this, a 10-centimeter cube for instruments. And there are lots of things that could be put there. And that's not what we're doing. The technology of getting something there, and there are lots of people in the lunar science business who would be happy to. I mean, I've had a number of people talk to me. Well, if you get this going to the moon, we'd love to do this or that or the other thing. So there are a variety of things that could be done. I mean, you can measure magnetic fields, you can measure ions, you can measure ultraviolet, infrared, lots and lots of things.
Got it. Question back there. Sarah, we'll give you the mic, and then we'll get to you.
What do you think is the future of manned spacecraft?
Of manned spacecraft? Yeah. Well, actually, a part-time Vermonter helped decide that. Ed Crawley, who was the chair of the Aerospace Department at MIT, has a house in Warren. He used to be the president of our glider club at Sugarbush. And he was the person who actually wrote that report on manned spacecraft, spaceflight. And it's basically a budgetary decision. They came up with the conclusion in that report that they need to be about $3 billion a year more towards manned spaceflight to talk about going to the moon and landing on the moon. But other people are thinking about why land on the moon? We've already done that. Why don't we do something different? And one of the things they proposed in that report is to go and land on one of the moons of Mars, which are very small and therefore fairly inexpensive from a spacecraft gravitational standpoint to land and take off again. So you could have people land on those and then have a robotic spacecraft landing on Mars. And there is some utility in that you could have astronauts sitting on the moon of Mars controlling the spacecraft on the ground with a very short radio delay. It's not feasible to control them from the Earth. They do certain things, but they can't have sort of up-to-the-minute control because of the time for the radio signals to get there. So this way, somebody who is nearby could control the thing that's going to land on the moon. It doesn't have to have the rocket energy to take off again with people and all of the support equipment. But I think that we're likely to have a continuation. Right now the Chinese are moving in that direction. And it's basically a matter of what we decide to do with our money. I mean, if the amount of money that goes into a manned space program, although it's not inexpensive, it's inexpensive compared to a lot of things. Just look at various weapon systems that are put together in the Pentagon. Many of which are not particularly needed, not even wanted by the Pentagon, but get put there because some congressman or senator wants a plant in his district to get lots of money and have jobs in his district. And so Congress has actually put weapon systems into the budget for the Pentagon that the Pentagon didn't want. And, almost any one of those would pay for a manned space program. So there is money. I mean, it's just where you want to put your money. But the technology, I mean, we already showed we have the technology. So it's just a monetary decision.
We're learning lots today. You got a question?
You're doing so many exciting things, and I guess my mind races to how what you're doing impacts other Vermont industries. And not to be too parochial about it, but microstrain is one. You've got Vermont's very much active in alternative energy. Yep. There's energy systems. There's defense contracting. To what degree do you have interactions with other Vermont industries, and is there symbiotic relationships with that?
Yeah. Well, so far, I mean, we have this thing with microstrain is one. They gave us some sensors, so that's an example. LED Dynamics will be putting LEDs on our CubeSat. And I particularly like that since they're all former students of mine that started this company, and it's a very successful company. They've been around for about 10 years. They have 30 employees in Randolph, and they're about to double their size. They make, if you buy some of the Philips LED light bulbs, the electronics in there are made by them. They make the power supplies for LED systems. And they already have stuff in space on the space station. And I have to go down and visit Vermont Composites in Bennington, who made the shrouds for the Taurus rockets, because we're going to be building, if we go to the moon, a carbon fiber spacecraft. And these guys have a lot of experience on carbon fiber spacecraft stuff. And so that would be another company that we could get involved with. We could get, again, the CubeSat industry is a small industry, but it's the kind of thing that some graduates from Vermont Tech could start a little company to make some, who worked on these projects. Oh, maybe somebody else, we could make the power supply boards better or cheaper than they make them in where do we get power supplies or Scotland? Got to remember. We have power supplies from Scotland, antennas from Holland, the radio board comes from Ann Arbor, the structure comes from San Francisco. So we're getting the GPS is from Canada. So it's a very international project. But again, when we get students involved in this, NASA is very interested in the STEM, science, technology, engineering, and mathematics workforce, that we're not producing enough people with degrees in those fields. And so there are scholarships. For example, Vermont Space Grant gave out 6 scholarships last year. 3 of them went to Vermont Tech. We had half of all the scholarships in the state. They would have given out more scholarships if there had been more qualified applicants. But people don't know about that. And so this is one of the things. And these are not bad. They're $2,500 renewable scholarships. So if you get them during your freshman year, you've got 3 years of $2,500 a year that you can get. There are fellowships for summer workshops at NASA, at various NASA sites. And students who work on a project like this, I mean, I don't want to encourage them to apply for those because we want them to work on our project. But I may be getting one of the students who worked at NASA last summer to now work on our CubeSat project. And since our project is hopefully going to be finished by the end of May, he could still do another NASA job this summer. So, there are opportunities. There are companies working on space stuff in Vermont that I'm sure I don't know about. I mean, I didn't hear about Vermont Composites until I heard about this rocket failure that happened to have CubeSats on it. If it hadn't had CubeSats, I never would have known that this company existed. And it has like 270 employees. It's a fairly good-sized company, for Vermont.
Any other conversation that we have here? Yeah, another question?
There's a lot of concern about space junk, and if CubeSats were to become really popular, there might be an awful lot of them.
Yep.
Is there any attempt to try to keep track of where they are and try to organize where they're launched and what their orbits are and all of that?
Yeah, that's they keep track of where they are and where they get launched, and the biggest issue is to have some way of deorbiting them when you're done. Most of the CubeSat missions are relatively short, months or a year or two, and so then they're not long-term space junk. And now, the higher orbit you get, and the orbits you typically get at CubeSats depend on who you get a ride with. You don't have to choose them yourself. So, some CubeSats have been launched at 600 or 700 kilometers. Not that they needed to stay up for 25 years, but they will. And then, at least there's a requirement that you can't stay up longer than that. It's still not great because there really is a lot of space junk, and it's a problem because if you get a collision, you create a lot more space junk. And there was a collision last year with an Iridium communications satellite was hit by a dead Russian rocket and made about 1,000 pieces of space junk instead of 1 or 2. This Iridium wasn't space junk; it was a usable satellite. But the Russian one was 1, and so that 1 became 1,000. And it doesn't matter how big they are; these things are going so fast that one little tiny piece can destroy something pretty big. So that is an issue, and I'm suspecting that there will be a requirement soon that when you have a CubeSat, it has to be deorbited fairly soon, right after your mission. So they're probably all going to be required in deorbiting mechanism. Right now, I mean, I had to fill out an orbital debris. This is a NASA thing. So we had because this is the first group of CubeSat. Well, ours is in the first overall group. There were actually 2 other launches, 1 failure and then 1 successful in November of CubeSats under NASA on NASA launches. That there's all the NASA paperwork to fill out. And most of it is really not relevant for CubeSats. It's for big satellites. But I had to fill out all these. I mean, I spent a lot of time filling out paper. And so one of them was an ODAR. NASA is full of acronyms. And so much so that at the CubeSat conference, you have both the NASA acronyms and then there are military people there, and you get the military acronyms. And so I was suggesting that we should get one of our senior students for a senior project to make an acronym translator. So you can use the commercial off-the-shelf voice recognition software, pulling it when you get groups of letters as an acronym. It then looks them up in a table, and on the presentation slide, it has the translation of all the acronyms down at the bottom. But anyway, so I look up ODAR. What the hell is this? So I look up ODAR, and ODAR is an ODA report. Okay, so it was defined with another acronym. And I then looked that up, and that's orbital debris assessment. So that's what they're looking for. They actually want to know what all the various components are, what metals and toxins and things like that. They're concerned because we have lithium batteries, so there's lithium in there. Well, the amount of lithium we have, when this thing deorbits and burns up, if it happens to land near somebody who's got bipolar disease, it'll make them feel better, but that's about all that it's going to do. We've got like 0.3 of a gram of lithium in the whole spacecraft. But that is an issue, and people are looking at it. It is a concern.
Okay, does anybody else have any burning questions or conversation or observations they'd like to make? No? All right, well, thank you very much for coming tonight. We hope to see you all.
Thank you. Thank you.